Hello everyone and welcome back to Math Made Easy. In the previous lecture, we started the Hermite interpolation method where we used both function values and derivative information to construct an interpolation polynomial. So today we are going to study another very important interpolation technique as spline interpolation method. So suppose we have a large number of data points, for example is x0, y0, x1, y1 and up to xn, yn. And one approach would be to construct a single polynomial passing through all these points. But as the number of points increases, the degree of that polynomial also increases. And a higher degree polynomial can become computationally complicated and may exhibit undesirable oscillations between the data points. So instead of using one large polynomial, spline interpolation takes a different approach. We divide the entire interval into smaller subintervals and construct a low degree polynomial on each subinterval. The individual polynomials are then joined together smoothly, and this is the basic idea about spline interpolation. So in today's lecture, we'll understand what spline interpolation is and why we need splines, the piecewise polynomial interpolation, linear and quadratic splines and cubic splines, then cubic splines and the continuity conditions, natural cubic splines, the system of equations for cubic splines, and a complete numerical example. So let's just begin. So let's first understand the problem with higher degree polynomial interpolation. So suppose we have only 3 data points and we can construct a polynomial of degree at most 2. And with 4 points, we can construct a polynomial of degree at most 3. And with the 10 points, we may need a polynomial of degree at most 9. But with many data points, a polynomial becomes very high degree. And this can lead to complicated calculations, numerical instability, and oscillations between the interpolation points. So instead, spline interpolation says, why not use several simple polynomials instead of one complicated polynomial? So for example, suppose we have this x0 lesser than x1, lesser than x2, lesser than x3. So instead of one polynomial over the entire interval as this we can construct s0x on x0 to x1 and this s1x on x1, x2 and this s2x on x2, x3. So each polynomial is relatively simple and together they form a spline. Now, the spline is basically a piecewise polynomial function defined over a sequence of subintervals. So, suppose we have knots, that is x0 less than x1 and lesser than up to xn. Then, a spline consists of different polynomial pieces as is s0x, s1x up to sn minus 1x. So, where this six is defined on this closed interval of xi, xi plus 1. So this Sx become Six, where this x belongs to this xi, xi plus 1. And the points are these x0, x1 and up to xn are called as knots. So there are several types of spline interpolation as this linear spline, where each interval uses a polynomial of degree 1 and hence this Six becomes ai plus bix. Now this quadratic spline, where each interval uses a quadratic polynomial as this Six equals to ai plus bix plus cix square. And then comes the cubic spline, where each interval uses a cubic polynomial as this Six equals to ai plus bix plus cix square plus dix cube. So among these all, the cubic spline is especially important because it provides smoothness up to the second derivative under the standard cubic spline construction. Now, you may ask why do we usually use cubic polynomials? So basically a linear spline is easy to construct, but the slope generally changes abruptly at the knots. And a quadratic spline provides more smoothness, but it doesn't offer the same standard level of flexibility. And this cubic spline allows us to impose the continuity of s of x or s dash x and s double dash x at the interior knots. Therefore, the resulting curve is smoother. So we can think of it as joining the individual polynomial pieces without sharp edges, without sharp changes in slope or curvature. And that is why cubic splines are extremely important in numerical analysis and computationally applications. So suppose we have this n plus 1 data points is x naught, y naught up to x and yn. And there are n intervals. On each interval, there is a closed interval xi comma xi plus 1. So we define a cubic polynomial there is six. And for a standard cubic spline, we impose the following conditions as is condition 1 says this each spline must pass through the data points. That means this six of xi, this si of xi becomes yi, and this si of xi plus 1 becomes yi plus 1. And at condition 2 says that at each interior node, this si minus 1 dash of xi equals to si dash of xi. And that means the slope is continuous. And at each interior node, this si minus 1 double dash xi minus 1 becomes equals to this si double dash xi. And this ensures the continuity of the curvature. The conditions above are not enough to uniquely determine all the cubic pieces, so we also need two boundary conditions as well. So one of the most common choices is the natural cubic spline. So for a natural spline, we take this s double dash of x naught equals to 0 and this s double dash of xn equals to 0 as well. So these are called the natural boundary conditions. So remember this natural cubic spline means the second derivative is 0 at both the endpoints. So a convenient form for the cubic spline on the closed interval is xi comma xi plus 1 is as six equals to mi times xi plus 1 minus x whole cube divided by 6hi plus mi plus 1 multiplied by x minus xi whole cube divided by 6 times hi plus yi minus mi hi square divided by 6 into xi plus 1 minus x divided by hi and plus this yi plus 1 minus mi plus 1 hi square divided by 6 multiplied by x minus xi divided by hi, where this hi is equals to xi plus 1 minus xi and this mi equals to s double dash xi. So for a natural cubic spline, m0 and mn both become 0. And this formulation is particularly useful for the numerical computation. For the interior nodes, we can take the mi values that satisfy the tridiagonal system. As this hi minus 1, mi minus 1 plus twice of hi minus 1 plus hi multiplied by mi plus hi times mi plus 1 equals to 6 times yi plus 1 minus yi divided by hi minus yi minus yi minus 1 divided by hi minus 1 for I equals to 1, 2 and up to n minus 1. Now notice something interesting. This produces a tridiagonal system of linear equations and we have already studied a specialized method for solving the tridiagonal systems, that is the Thomas algorithm. So this connects directly to the earlier part of our numerical analysis roadmap. So we have a quickish question here where we need to construct the natural cubic spline for the data as given in the table form as is x and y values, x as 0, 1 and 2 and y as 1, 2 and 3. And now you need to determine the spline value at x equals to 0.5. So you have already this x0 value as 0, x1 as 1 and x2 as 2. So therefore your h0 becomes this 1 minus 0 as 1 and this h1 is equals to 2 minus 1 as 1. So for a natural spline, we have taken this m0 and m2 value as 0. So there is only one interior point left, that is this m1. And using the condition as this h0 into m0 plus twice of h0 plus h1 times m1 plus h1 times m2 equals to 6 times y2 minus y1 divided by h1 minus y1 minus y0 divided by h0. So we obtain this as this 1 into 0 plus 2 times 1 plus 1 m1 plus 1 into 0, which becomes equals to 6 times 3 minus 2 divided by 1 minus 2 minus 1 divided by 1. Therefore, your 4m1 becomes 6 times 1 minus 1 as 0. That means your m1 again becomes 0. So your all the 3 mi becomes 0. And since all mi are 0, the cubic spline reduces to the linear pieces. So for x that lies between 0 and 1, so we have this s naught x value and this 1 plus x minus 0. So your s naught x becomes 1 plus x. And for the x that lies between 1 and 2, we have this s1x equals to 2 plus x minus 1 as x plus 1. Therefore, this spline becomes this s of x as 1 plus x and 1 plus x, where x is lying between 0 and 1 and x is lying between here 1 and 2. So in this particular example, the data already lie on the straight line. Therefore, your s of 0.5 becomes this 1 plus 0.5 and your s at 0.5 becomes this 1.5. So far we have started the spline interpolation method. We learned that instead of constructing one high degree polynomial through all the data points, spline interpolation divides the data range into smaller intervals and constructs a lower degree polynomial on each interval. And we discuss the linear splines, quadratic splines, cubic splines, continuity conditions, natural cubic splines, and the system of equations required to determine the spline. So the most important idea to remember here is a spline is actually a piecewise polynomial only. And for a standard cubic spline, we impose the continuity of s dash and s double dash at the interior nodes. So for a natural cubic spline, you have the boundary conditions at the boundary points as is s double dash x naught and x double dash xn becomes 0. So one particularly important connection is that the equations for the unknown second derivatives from a tridiagonal system. And that means the Thomas algorithm that we started earlier can be used to solve the resulting system more efficiently. So with this lecture, we have completed the major interpolation methods in our roadmap: the Lagrange-Newton forward method, Newton backward method, Newton divided difference, Hermite interpolation, and hence spline interpolation. And in the next lecture, we will move towards the next major section as numerical differentiation. We will begin with the first derivative formulas, including the forward, backward, and central difference formulas. We will learn how derivatives can be approximated when we have only the tabulated data of a function. So thank you for watching, and if you found this lecture helpful, don't forget to like, share, and subscribe to Mathmate Easy for the complete numerical analysis course. Until next time, keep learning, keep practicing, and keep questioning, and I'll see you in the next lecture.